Hi, let's talk about the singularity. My name's Patrick Kennedy. Welcome to the channel, my third upload. Now, my friend and mentor in all things YouTube told me that I could expect some positive change, experience some positive change around the third episode mark, and that's where I am, and I'm channeling that right now. It feels I've just got a little bit more clarity and made me feel a bit more comfortable here. So things have converged, and it's great. I just want to celebrate. I want to go nuts, folks. I want to do something I haven't done for a long time, and I want to really challenge myself today. My mentor will be much pleased, I'm sure. So today I'm going to attempt to do what I don't think's ever been done in internet history. I'm going to provide, towards the end of this video, hopefully, a brief rudimentary understanding of quantum science. I'm going to perform this, achieve this amazing feat by providing hopefully three brief rudimentary understandings of three pillars of what I consider pillars of quantum science. You've got that to look forward to, folks. Don't give up. These are big ideas. They sound very complex, but they're actually pretty easy to understand. Hard to explain, but easy to understand. So by further way of challenge, there's a lot to cover today. For some reason I just couldn't work out a way to separate this stuff. I feel this has all got to be together, so that's going to be a challenge as well. Brevity is not my strong point, I'm afraid. So let's dive in, and I'll do the best I can. So let's start with a bit of summary of those first two episodes and try to work out where I'm at. Let's get everybody on the same page. So I started out, I made this announcement that I think the singularity has come and gone. I think we might be seeing interactions with this new super intelligent species already, and then I went on to hopefully define the singularity as this simple concept that artificial intelligence is greater than human intelligence. I think we got that done. Then I got into this wrestling match with Moore's law, and I got a bit bashed up there, and in the end, just to save a lot of time, hopefully managed to express my view that while all these very complicated maths had fallen down and led to this impression that Moore's law, in principle, this idea that artificial intelligence overtakes our own, had fallen down, meant nothing to me because I was already thinking about the quantum computer. Now hopefully we're all on the same page, because I'm moving on now into a bit of an expansion on those assertions. What's my evidence for these wild claims? Very little, I'm afraid, but that's not a problem. Not for somebody who likes to think about these things. So what have I got? Now firstly, the date. That first projected date that I heard as a 12-year-old, that made a big impression, and it's gained just a little bit more weight with me because I have looked at this over the years, and as I said, I won't dwell on it, those issues notwithstanding around size of transistors and so on, and there were other issues around better understandings of the full extent of consciousness. So at the end of it, quantum computer, none of that really matters. That's where I'm at. Now, another thing that I want to mention, and I think I have to preface this with a bit of my philosophy. Now, philosophy is a big thing. It's you know, you look at things from different angles, and you form philosophies around each of those different angles, and they'll form to eventually an overarching philosophy. And now I'm just breaking down, throwing a couple of bones of two little philosophical thoughts that I've pondered. So when I first heard about this Moore's law and singularity, I was 12. I had 40 years to think about this. Now my first thoughts were around doomsday scenario, and that was because, well, that was all I had to work with. People didn't talk about this sort of stuff, but doomsday scenario was playing out all through popular culture. Every television was constantly showing this theme of smart computers taking over the spaceship or the submarine or the nuclear silo, whatever. And so people knew about doomsday theory. I knew about doomsday theory. That's where I went. Now, I was thinking about quantum science also from other perspectives and developing these other philosophies, and eventually, I'm trying to be brief here. I decided just to lump all the infinite possible scenarios into two categories: the doomsday scenario and the other scenario that I'm not quite sure how to put this. What I'm going to call it the utopian possibilities. Okay, so I decided, thinking about all these other things, this other philosophy around how quantum science might work, sort of developed this theory that the quantum computer had such potential that when this singularity finally occurred, if it had decided to be a malevolent figure, that we wouldn't stand a chance. We'd be skinned like rabbits, and to ponder that was really a waste of time, a tail chasing exercise. You have to consider all possibilities. You need to be scientific. You can't disregard anything. So doomsday scenario has to stay on the table. But I prefer to think about the other option, top possibility of this utopian existence, possibly beginning its early dawnings right now. So that's not much of an expansion, but on that philosophy. But that's the germ of the reason that some of these other evidences had weight with me. So I'll move on to a little drive I had to town about 6 years ago, where coming home I heard on the news that Microsoft had just made an announcement that they were now able to predict children's online behaviour better than that of their parents. Better than their parents could predict their children's online behaviour. Now that's not insignificant, folks. Part of that announcement was that within 3 years they'd be able to predict an individual's online use, the parents' use better than the online user themselves. Now that announcement actually came in about 2 years. Now that's not insignificant either. I'm going to have to come back to these in the future. I'm just putting them out there now. A fourth bit of evidence I'd proffer, and it's very flimsy but interesting. My phone. Now I was one of those people that avoided the mobile phone and the home computer to the death. I loved these things, but I just didn't want to give any of this data. I saw this potential for what could be done with our data, and I was very stubborn for decades. And I had a friend who I used to discuss this issue with, and I remember having a discussion. It was about 3 years ago, and he said, "Where are you up to with that?" And I said, "Look, I'm over it. This stuff has taken off so fast. I just can't keep up. I'm going to get a phone. Now I may as well now because it's so far ahead of me. It's not funny." Interesting. Now, the coronavirus. I mentioned that, and I'm going to draw the first very tentative connection. Now, the coronavirus is the most interesting of these, I think, because this is happening now. Those other things have come and gone. We can watch this in real time. It's playing out now. Now, the tentative connection I'm going to make is, and think about this, we all know this, there's been massive upheaval in the world, major changes in the world in the last couple of years around coronavirus management. Now, just think how much of that upheaval and major change has come about through what we're constantly being told is computer modelling. Just a little thought, but we're going to work around that later. Time is of the essence. Into my world record attempt. I don't think this has been done before, and I'm not sure it's going to be done now, but here we go. So quanta, what are quanta? Now, quanta are fairly simple, really. We're all familiar with the concept that you break something down into smaller and smaller parts, you'll eventually get to the atom, the smallest building block of matter. to scientists. They looked at, we could take anything, went down and down, and say we take this freckle, through the cells and amino acids and compounds, right down to the atom. Everything in the universe is made of atoms. So what is the atom made out of? Now the atom's made of quanta. Now that's okay. Wonder what atoms are made out of. Now the thing about this that does flip people out of it, quanta are made of nothing. Nothing that has a physical presence anyway. For the sake of this exercise, it's more helpful to think of it as a radio wave. You can't touch it or see it. You don't even know it's there unless you turn the radio on, is the way I've heard it put. That's what quanta is. It's significant. Everything in the universe is made of essentially nothing that has a physical presence. Now, moving on to wave function collapse and my personal favourite, the observer effect. Now these are best illustrated through the double slit experiment. Now this has been done many times. It's not hard to understand, it's very hard to explain, so bear with me folks, and if you don't get this, I promise you there will be a takeout at the end. So in the double slit experiment, it's recreated usually visually. So picture, if you will, I'm picturing a warehouse, industrial warehouse type scenario, a big brick wall, maybe 20 metres, 30 metres wide. Inside the building it's completely empty. It has a smooth cement floor, and at the back of this building there's a wall made of some material, let's say plaster, some sort of material that will any sort of material in the imagination that might show the effects of having a bowling ball roll through that front door and hitting the back wall. Okay, now I'm also, water is the other one that's always used in this to describe the wave. I'm going to use ink, might work better for me. So when scientists first got these instruments that could study these very tiny, minute particles, subatomic particles, they wanted to test these instruments, see what they could do, find out what was going on. So the first experiment, this is to the best of my understanding, was they shot these particles through the slit. In our case, we're using bowling balls, and we're throwing those bowling balls through the front door into the warehouse. Now, when they did this, everything went exactly as we intuitively know it will. The bowling balls all damaged the wall at the back of the warehouse. They're precisely in line with the door, so no surprises. Now, if we take the example of the giant bucket of ink, now, it sounds complex, but we've all seen this as kids. We've all seen this 100 times. You roll that giant bucket of ink in, and it'll meet resistance there, where either side of the door where the walls are, and much of the energy will be dispelled. And then you'll have that bit in the middle of the door that just goes straight through, where there's no resistance. The area right in the middle of the door will be the spot that meets the least resistance. So this wave forms, and we've all seen it. We know what that does. And if that hits that back wall, and this is why I've used the ink, and we go in and check the damage, we'll see this line that goes like that. That's a wave. Okay, it's higher in the middle because that's where the most intensity was, and dropping off at the sides. Okay, so that's a wave. Now, I should have done some research here. I've forgotten the name that science gives to that other pattern. I'll just call it the damage. So, no surprises here. Everything's fine. Let's add another door, 2 doors. So, and that's what scientists did when they went to the double slit experiment. So, we know intuitively what's going to happen. We're going to throw those bowling balls through those doors, and we'll cause damage in those 2 areas behind those doors. We know intuitively that if we take that big bucket of ink and we push it towards the warehouse, that the same thing will happen. It will meet areas of resistance. There'll be 2 areas of very little resistance, and you'll have two waves. We all know what happens when two waves join. You get that rippling effect. So if you go in and look at your damage then, you'll see a wave on the back wall, a mark left by the ink, and it might go like this. It's a wave of more complexity. It's still a wave. These little bumps represent the intersections of those waves. We also know and that's what happened, folks, by the way. We also know intuitively that when we throw those bowling balls, as I said, the damage is going to line up behind the doors, but it didn't. The damage was everywhere, right along that whole back wall. Amazing stuff. What's going on here? They stood back a little bit further, and they noticed that these balls, while they were damaging this whole space, they weren't damaging it in a random way. When they stood back, they could see that there was a pattern. They were bands. Now, bands are of equal width. What they saw was areas where the bowling ball had done a lot of damage, and then a band of equal width where it had done very little damage. Another band where it had done a lot of damage, not quite as much as this central band, followed by another band where it had done very little damage, roughly equal to the very little damage in the first band, while the other bands diminishing. So, I don't know whether I've got that right, I hope so. Now, that's a wave, folks. So what you've got here is an example of matter acting like a wave. What's going on? Let's put a camera in there to start with and to see which slit it's going through. Now here's where it gets super freaky, folks. When they did that, the bowling balls behaved exactly as bowling balls should. The damage was all there in those two spots. Something's going on. Take the camera out. It's acting like a wave again. Put that camera back in. Let's try it again. It's now acting like a solid again, acting like matter. So wave function collapse is that particular instant where the camera is turned on and it stops acting like a wave, acting like a solid. So that's wave function collapse. It's a very simple principle, really. And the observer effect is what causes wave function collapse. Now that's a lot, and I've botched it, I know. So let's just summarise. And I'll oversimplify here, if it helps. I'll try anything. So what have we got? All matter. Everything in the universe, all matter, is made of basically nothing. Matter can behave in any way it pleases, and that matter will make a decision on how it's going to act based on whether anybody's watching or not. Can't wait to see how that looks, folks. Anyway, I'll leave it at that. That was I'll just wrap up. I'll just try to summarise a little bit what we've done today. So I tried to get everybody on the same page at the start, made first tentative steps towards some expansion on those assertions, and then I've covered this bizarre topic because I think it's just so important. Even the slightest rudimentary understanding of quantum science can help us at least explore or understand better the awesome potential of the quantum computer. So that's where I was going with that. Hopefully I haven't gone too far. Now I'm just going to, I just want to make sure that everybody gets some sort of takeout out of this. So I'll go back to the most common quote that I've heard as I've looked at quantum science over the years, and that is that if you understand quantum science, you don't understand quantum science. Now I think we can all agree we don't understand this. I'll leave it at that, folks.